Combustion engine vehicles are a leading cause of climate change and harmful emissions. At Group 4 Consulting, we are promoting sustainable innovation by competing in a mini solar car drag race. This event helped bring the ideas behind alternative energy to the public in a new and exciting way. For our problem definition, we were tasked with designing and building a mini solar car to race across a 1-meter track. Sticking with the spirit of the competition, we were incentivized to keep the embodied emissions as low as possible. With a budget of just $25 and a kit of test parts, we set out to win the competition. After doing some research into solar cars, our team used the 365 method as well as morph charts to select the best components for the car. The main components we considered were panel placement, wheel design, and chassis type. After ruminating on these ideas for a few days, we came together as a group and decided on 4 fleshed out ideas. Design 1 was a 3-wheeled wooden ladder chassis designed for low weight and to go as fast as possible. Design 2 also used a wooden ladder chassis, but focused more on keeping emissions low with only 1 solar panel. Design 3 used multiple motors in a wooden block chassis, designed to house multiple panels for maximum power. And Design 4 utilized a lightweight 3D printed chassis, a custom weight holder, and panel mounts to deliver a balanced and fast car. Ultimately, Design 4 was selected because of its aesthetically pleasing design and high power-to-weight ratio with minimal embodied emission. Once our working drawings were approved and we had our first physical model, we got to testing. Our first iteration had issues from the beginning, everything from broken supports to poor power delivery to the motor. However, it was not a total failure, as our wheel design proved effective and our overall fitment for the car was excellent. To address the issues, we went back to the 3D printer and the wagon was born. Once reprinted, our final product had stronger supports and a better power system via 3 smaller solar panels connected in parallel. Compared to the kit car, our custom 3-wheel design had lower rolling resistance, and combined with improved power system, it raced down the track much faster. To quantify our progress, we conducted an analysis of the impact of how additional weight impacted the car coming down the start ramp and found that additional weight improved the time. We also conducted tests to see how the lamp positioning affected the speed of the car. However, during testing, the motor wires became disconnected, and once rewired, we realized that the car ran backwards as we had rushed to put it together. At that point, we decided that this direction was actually advantageous to us as it let us produce more power early on. So much power, in fact, that the wheels were spinning. A lot. To remedy this, our team cut up some balloons and stretched them over the drive wheels. After all the optimization, our car would do a meter in 0.75 seconds. Race day came and we were ready. The team snapped into action, setting up the track, lighting, and car for the ultimate performance. We went face to face for 5 races and came out on top, destroying the competition every time. It was clear that our car was purpose-built for speed and not looks. As compared to our competitors, the aesthetics of our car were sorely lacking. While the car's power to weight led us to winning the competition, we found a reduced amount of embodied emissions would have provided a faster and more environmentally friendly car. Looking back on the project, there are several things we would have done differently. For starters, we would have spent more time researching and testing electronics to get the optimal power system the first time around. Knowing the components we were going to use early on would have allowed us to incorporate them in a much more aesthetically pleasing way. In the end, we accomplished both of our goals. Our design won the competition and in the process promoted alternative energy use.